Hello, everyone. Welcome to this webinar on running stateful workloads on Kubernetes in production, brought to you by Portworx. So if you're attending the MI2 webinar series for the first time, let me take a minute to set the context. MI2 stands for Machine Intelligence on Modern Infrastructure. And this essentially covers two emerging technology trends. One is the machine intelligence that essentially covers artificial intelligence, neural networks, cognitive computing, Internet of Things, and edge computing. And the modern infrastructure is all about Kubernetes, cloud native, service mesh, cloud native storage, cloud native networking, and so on. Every alternate week, I bring one of the sessions from these two tracks. There is a tremendous opportunity in the market for the convergence of machine intelligence with modern infrastructure. So Kubernetes is emerging as the foundation of modern infrastructure, and TensorFlow and the AI related technologies are becoming the #1 workload that are going to run on top of Kubernetes. And the idea of MI2 is to bring you the overlap and the convergence of these two important and emerging trends. Unlike other sessions, MI2 typically comes with a hands-on demo and also a complementing tutorial and links to GitHub repos, code snippets, configuration files, and so on. And this webinar is not an exception. Right after this, when we upload the video to YouTube, you'll actually see the links to a step-by-step guide of the same demo that I'm going to show you. And today joining me is Michael Ferranti from Portworx. He is VP Marketing, and he's going to give us a quick overview of what is cloud native storage and what Portworx is offering. And then I'm going to come back and walk you through a live demo of running a production workload on Kubernetes, where I walk you through various steps of performing day two operations of running a production database. So it's my pleasure to have Michael join us. Michael, all yours. I'm going to turn you into a presenter.
Thank you, Janika. I'm really excited to be here and to be sharing with your audience. Let me go ahead and share my screen. Let me know when you can see it.
Yes, we can see that.
Okay, great. So I think that's an excellent intro and really right on the money, which is that Kubernetes is a new way of running any application, but often in paradigm shifts. Technologies are used to really accelerate certain classes of workload that were really just hard to run before in a traditional way. And I think AI and machine learning workloads are a good example of that, which is without a paradigm such as Kubernetes and distributed computing, it's much more difficult to build and run and scale those types of applications. And so Kubernetes has turned out to be kind of the perfect solution for it. And you could argue that the killer app for Kubernetes is going to be the AI-driven workload. So as a company that specializes in kind of production operations for enterprise applications, we have a lot of customers who are running those types of workloads on Kubernetes. And my presentation today is really about solving a lot of the things that kind of go around the artificial intelligence app itself. So you're going to show a demo of actually how you run the application. I want to talk a lot today about what are the things that you might not want to think about, but you're going to have to anyway if you're going to be successful running those types of applications on Kubernetes. And there, I'll just mention briefly one thing like data security. You have to, when you have a rich data set that you're going to extract business value out of, you have to realize that that's both an asset and a risk, and you need to be able to manage that. And there's a lot of automation that can be applied to Kubernetes that allow you to manage the risks inherent in running these types of applications in ways that don't put your business at a disadvantage. And kind of when you do all of those things, kind of the infrastructure gets out of the way, and you can get the benefit of the app itself, of the business intelligence that the application is providing, and thus not kind of just have to live in this persistent state of being an expert at running infrastructure, but rather becoming an expert at using the intelligence coming out of the application. So with that long-winded intro, I'll transition to just a little bit of context setting, and I alluded to some of this just a minute ago. There are really some unique pressures driving cloud native in Kubernetes generally. The need for speed is one of them that every industry is at risk of being disrupted by a quicker and nimbler startup, right? It's the fast eat the slow. It's not only the big that eat the small now. At the same time, you have this massive data explosion occurring that, as I mentioned, is both an opportunity but also a threat. And having threats of ransomware, data exfiltration, the list goes on, and there are even broader security threats that are happening as well, social engineering and other things that are just putting enormous pressure on organizations to figure out how they can move faster, how they can take advantage of and protect their data and respond to ever increasing security threats. When we look at, okay, how do we solve this puzzle? How do we deal with these competing pressures, right? If we want to move fast, then we say, well, let's eliminate risk, right? But when we eliminate risk, then we tend to move slower, not faster, right? Or excuse me, if we want to move securely, we eliminate risk, but then we move slowly. So it's not obvious how you balance those three. Well, a pattern has emerged. That pattern is cloud native technologies. That when you build apps using containers, using Kubernetes, you can both move faster, you can move more securely through automation, you can take advantage of many different solutions that were custom built for AI and ML workloads, right? That allow you to accelerate even further. It's kind of the best of both worlds, and because a new pattern has emerged, a new stack has emerged, right? You've probably seen the CNCF ecosystem landscape, and it's probably 300 to 500 projects at this point about what it means to be cloud native. Very, very confusing. Lots and lots of choice. But if you simplify it down, if you boil it down, there's this new stack that's emerged, built around Kubernetes, that's pluggable for key parts of the stack like storage, networking, monitoring, security, built from the ground up to run across any environment, right? Any cloud, any on-prem data center, edge locations, right? The list goes on, and that stack has a number of benefits. It radically simplifies the operation of highly scalable distributed systems. It gives us a self-service experience for our developers, right? Instead of filing tickets, we just deploy YAML files, and we suddenly have the infrastructure that we need. We can take advantage of automation, which, as I've alluded to before, solves a lot of security problems. Much lower touch operation. The list goes on, which are in terms of benefits. In fact, that's probably why you're here today, because you've heard about the benefits of Kubernetes and you want to learn more. Now, all of those benefits only go so far as the apps that can run on Kubernetes. So if you think about your organization and what is the total universe of all of the server-based applications that you run? If you can move 5 to 10% of those to Kubernetes, but not the rest, then just how important is Kubernetes to your overall strategy? I would argue not much, right? I'd use the example of VMware and say, when VMware started, it was a point solution for doing virtual desktops or test dev environments, right? But fast forward to today, and 80 to 90% of the enterprise data center is virtualized. That's because VMware as a platform was able to run any enterprise application. And so when we applied the benefits of virtualization, we could apply it at the entire data center level. It suddenly became something that CIOs were interested in, right? That CTOs were interested in, because it solved problems for all their apps, not just a few applications. And with Kubernetes, we're at a point today where Kubernetes is great for certain classes of applications, but applications that have business requirements related to data don't run well today on Kubernetes alone. Kubernetes alone, right? It's a rich ecosystem. We're going to show you how to do it. But if you just pick up the Kubernetes core and you try to run, say, a database, and you have sensitive user data, or that database is very performance intensive, or you have a DR requirement, or you have requirements from a governance perspective around role-based access control, the Kubernetes core itself doesn't solve those problems. You need to go out into the ecosystem in order to find technologies and solutions to solving the business requirements associated with those types of applications. Our argument is, when I say our, I mean Portworx. The Portworx argument is that in order to move from running a small subset of our applications on Kubernetes to all of our enterprise applications on Kubernetes, you need a Kubernetes storage platform, right? And again, I'll reuse the VMware analogy. What I'm saying is that to go from Kubernetes being a point solution for something equivalent to the VDI workload, an important but a very small subset of overall use cases, to 80 to 90% of our enterprise applications running on there, you need to be able to solve the storage and data management problems that come with most enterprise applications, right? There are three reasons for this. One, all enterprise apps have data, and that data always needs to be available, performant, and secure. At the same time, yesterday's storage, right, your traditional enterprise storage cannot keep up with the scale and the dynamism of Kubernetes environments, right? It's just a different ball game when you start to move into Kubernetes. And as much as we want to simplify as engineers, we can't just ignore the problem. We can't say, okay, let's carve up our application and let's run the stateless components over here and let's run the stateful components over there. That just increases complexity. It increases cost, lock-in, and at the same time reduces agility. So what does a successful Kubernetes storage platform give you? Well, it gives you something that looks like what I'm showing here. It's a broad range of services that solve large classes of business requirements that are just very common with enterprise applications, right? If we have an enterprise application, we have to think about backup and we have to think about recovery. It's non-negotiable. We can't kind of do a give and take with the business team. If we're going to take an enterprise application, we're going to put it on Kubernetes, then there's got to be a backup, right? Especially if let's say there's consumer data and we're thinking in terms of GDPR, we're thinking in terms of CCPA, there just have to be backups. It's non-negotiable. Data security is another one. Capacity management is another one, right? Kubernetes can infinitely scale our applications, but our infrastructure needs to be able to keep up with it. So a Kubernetes storage platform kind of gives you the ability to take arbitrary enterprise applications and run them successfully on Kubernetes by solving the things that we've already solved for a decade on VMware, but where those solutions don't fit within a Kubernetes environment. So at this point, you might be saying, well, okay, I get it. These are business requirements that I have in my organization. And yes, in order to run an app on Kubernetes, I need to be able to solve them. But I've already got enterprise storage. I don't understand why I can't just use that. My NetApp has a Kubernetes plugin. Why can't I just use that? The reason is just because a storage system connects to Kubernetes doesn't mean that it is Kubernetes native. Doesn't mean that it's a Kubernetes storage platform. I'll give you a couple of examples. We talked a little bit about existing storage not being able to keep up with the scale and the dynamism of Kubernetes environment. We have a customer today who's running over 15,000 volumes on only 16 EC2 instances in the cloud, right? That's a level of scale that I'll say is impossible to achieve with EBS alone, because you're limited to 40 EBS volumes per EC2 instance. It would be very, very challenging to achieve with any other software-defined storage system. software-defined storage systems based for VMs were just not designed to handle that type of scale. And if you think about taking that scale and then doing something like a Kubernetes upgrade, where you're going to do a blue-green deployment, you're going to, install a new Kubernetes cluster, you're going to test it, then you're going to migrate all of those 15,000 applications to that new cluster. That is a ton of concurrent connections that are going to happen all at once. Very, very difficult for traditional enterprise storage systems that were built to be managed by human administrators to be able to keep up with the scale and the dynamism of a Kubernetes cluster when you're talking about that many volumes, that number of concurrent operations. The next point I'll make is that Kubernetes gives us a new language for managing applications that's different from the language we used to use to manage virtual machines, right? From a storage perspective, virtual machines would have LUNs provisioned to them. If you're old school, you'll have heard that word. If you're cloud native, you won't even know what that word means. Point is, it's a key architectural element for a virtual machine when it comes to storage. Kubernetes doesn't have a concept of a LUN. Kubernetes understands pods, it understands applications, it understands PVCs. And the important point is that there's no translation layer between a Kubernetes concept of something like a namespace, right, where I can have multiple applications, multiple pods, multiple volumes organized into this logical grouping called a namespace that runs across multiple hosts, to then some underlying storage attribute like a LUN. There is just no equivalent. There's no translation layer. And so if you want to take a storage system that was designed to manage LUNs and then connect it to Kubernetes, there's going to be a disconnect. You're not going to be able to do something like back up a namespace using a traditional VM-based backup approach, simply because there's no translation layer. That's what I mean by lack of being Kubernetes native. The next point is another important one, and it relates to this application-centric view that Kubernetes provides. It used to be that we would run a single application on a single VM, right? We did that after we were tired of running a single application on a single physical server. So we virtualized, but we kept this model of a single app per machine, right? It was only now was a VM instead of a physical machine. That model completely breaks down within Kubernetes. Now single applications regularly run across multiple machines. And if we're going to back them up, if we're going to migrate them, if we're going to encrypt them, we need to be able to do it at that application granular level, not as a collection of machine-based snapshots or machine-based encryption keys. That model simply doesn't work. We need technology that can go in to a multi-tenant environment and control just the objects that we want to be able to control, right? And we want to be able to do that using the Kubernetes language of pods and namespaces and tags. The next point is that, there's been a lot of innovation in the container native space around storage and data management. Portworx is doing a lot of that, and other companies are doing a lot of that. It's really exciting to look at. But when you look at enterprise requirements, there's a very high barrier of business requirements before an app can move over to Kubernetes. Persistent storage, which there's a lot of discussion about, is only one thing you need to solve, right? You do need to be able to dynamically provision volumes at a container granular level. But just that isn't enough. You also need to be able to do backup. You also need to be able to do DR. You need to be able to provide data security. You need to be able to provide traceability and governance from a compliance perspective. It's only when you do a collection of these things that those apps, a majority of those apps, can run on Kubernetes. And then finally, all of this needs to be optimized for a multi-cloud world. You need to be able to run these applications in any environment, any cloud, hybrid, multi-cloud, etc. So it probably won't surprise you at this point that what Portworx provides is the Kubernetes storage platform for the enterprise. The Kubernetes storage platform designed for applications that must be able to run in production, that must be able to run with the same level of reliability and security and data protection as traditional enterprise applications, But where teams need to be able to automate, they need to be able to manage via Kubernetes. They need to be able to manage at an application granular level. That's what the Portworx Enterprise Storage platform for Kubernetes provides. We, to our knowledge, are the most widely used Kubernetes storage platform on the market. We work with some of the kind of most innovative and largest and well-known Kubernetes users in the world. We're really proud of that fact, and the reason I show this slide, it's to be honest with you, it's a little bit because I'm just really proud of it. The other reason is I want you to understand that no matter how complex you think your use case is, chances are we've helped another customer through it before. And we do it ourselves, and we do it with some with our partners. Just a couple of quick case studies, and when I say case studies, I promise I'll go through these really quickly because I want to jump into Gina Kiram's portion of the webinar soon, because I want you to see hands-on just how easy all of what I've just said is. I keep talking about production, I keep talking about business requirements, and that can lead you to think it's really complex, but actually it's quite simple. When you build something purposely for a particular use case, it's amazing how much you can accomplish in such a kind of elegant fashion. But just to give you a sense of customers who have been down that journey, where did they end up? I want to talk through 3 quick case studies. So the first is a large bank in North America who was running on Kubernetes for a number of years, really getting a lot of benefits out of it, started to say, hey, what other apps can we move onto the platform? And it turned out that they had an application that was a really good candidate, except it had a 0 RPO disaster recovery requirement, meaning they needed to be able to survive a complete data center outage and still recover their application to another data center with 0 data loss. Long story short, Portworx, we listened to the customer, we understood their requirements, and we engineered a solution that would become PXDR for this customer. And what it's enabled them to do is set up a single Portworx cluster spanning multiple data centers with synchronous replication between those data centers, a replication of all of their application configuration. So when they lose an entire data center, they can fail over their Kubernetes cluster to that second data center with 0 data loss. All of their application configuration is already there, and thus their RPO itself is less than 2 minutes. Our RTO, excuse me, is less than 2 minutes. In addition to having 0 RPO. Excuse me. The next example is T-Mobile. So T-Mobile is one of the largest mobile carriers in the United States, and their use case is really interesting because they're building a platform as a service for internal IT applications that power their in-store experience. And yet, because they're one of the largest mobile providers in the country, that internal Paas application actually has some elements of consumer scale to it, right? They see large spikes in usage when new iPhones are launched or Apple Watches, and they get a lot of kind of foot traffic into their stores for people wanting to buy these devices. So Portworx was able to help them solve the infrastructure problems associated with scaling that type of application. I talked about capacity management earlier, right? You have to think about, okay, Kubernetes can scale my apps, but how do I scale my infrastructure to match that? Portworx solves those types of problems in addition to your kind of classic persistent storage for container issues that we alluded to earlier. The last example is Esri. So Esri is a great example of kind of an innovative company that's really doing a lot around machine learning and artificial intelligence. They do a lot of IoT analytics. So if you have a large number of physical plant devices, whether that's taxi cabs or supply delivery trucks or even farm equipment, things like that that you need to keep track of in real time, Esri provides a platform for doing that. They were faced with an issue of wanting to build a scalable SaaS platform for a mass market, doing it on the cloud because that's where you build applications these days, but understanding that the cloud itself is fundamentally unreliable at an individual server level, right? Collectively, you can get quite high levels of reliability, but each component itself is highly unreliable. So how do you do that? Well, Portworx, with our software-defined storage layer, was able to provide reliable, performant, and secure storage for Kubernetes on top of unreliable cloud hardware, enabling Esri to scale their platform to the levels that they need without sacrificing performance. Okay, so you know what? I'm gonna call an audible here, and I'm gonna skip over these next couple of slides because I think Janet Kiram is really gonna do a good job of explaining exactly how Portworx works. I'm going to instead just go through about 3 more slides, and then I'm going to turn it over to Janet Kiram. In terms of the data services that we support, so you know what apps do we provide data security and backup and recovery and disaster recovery and governance and migration for? Well, it's anything that runs on Linux. Some of the most common examples are the ones that you see here. You know, MongoDB, Cassandra, Kafka, MySQL. I believe we're going to see a MySQL demo, and we do it in any environment. As I mentioned, I think Janet Kiram's going to show a demo on GKE, but we actually run on, first of all, any Kubernetes platform. So you could be OpenShift, you could be GKE or EKS or IBM Container Service, and we also run on any storage hardware. So from an infrastructure perspective, any cloud. But if you have a data center and you're using NetApp, that's awesome, right? We don't, just like we're not going to require you to pick Dell servers if you're using HP, right? That would be nonsensical. Why would you have to switch your physical compute hardware? We're not going to make you switch your storage hardware, right? If you're using and you love NetApp, great, continue to use NetApp. If you like Pure Storage, great, continue to use Pure Storage. You can take those existing storage investments and use Portworx on top of it. In terms of our platform, the first level is called PX Store. A PX Store is our software-defined storage layer. This is where you're going to do dynamic volume provisioning, high availability, local snapshots, a class of service, etc. This is how you can provide that scalable storage for any application without sacrificing performance. PX Central is our UI into all of your Kubernetes clusters that are running stateful applications. This is where you're going to go back to over and over again to interact with, to manage your clusters. PX Store provides encryption for data at rest and in flight at a container granular level, as well as role-based access control, so you can be assured that you can run sensitive user data apps on Kubernetes. PX-Migrate is what's going to enable you to migrate applications within a single environment, say as part of a blue-green deployment, as well as between environments. And importantly, Portworx always moves data and application configuration whenever we do a migration. So you don't have to think about long recovery times or rebuilding applications in place. Once the migration is complete, you simply start your Kubernetes containers and you're ready to go. Autopilot provides automated capacity management. I mentioned that earlier in terms of T-Mobile, right? Scaling your infrastructure to meet the demands of your Kubernetes scale. PXDR, it's what I talked about in terms of the banking customer, RBC, right? Zero RPO, disaster recovery between multiple data centers. We also support disaster recovery over the wide area network when your latencies are greater than synchronous replication can support. And finally, backup. Backup is all about point and click, ease of use, backup to any location, restore to any other location, protect your investments, make it really easy to meet your compliance needs. With that, I am going to turn it back over to Janet Kiram, and hopefully we'll be able to join back at the end with some questions. Thank you, Janet.
Awesome. Thanks so much, Michael. So just to wrap up the discussion around Portworx and what Michael was alluding to. So we are actually at a pretty interesting phase of the adoption when it comes to Kubernetes. And as Michael has been mentioning, this is almost like history repeating itself. When VMware became prominent and when it matured from being a simple hypervisor provider to a data center virtualization company, there was a whole ecosystem that was built around VMware, and it created a parallel IT industry whatever existed for on-premises physical data center slowly evolved, transformed, and matured to become virtual and to embrace the VMware and the ESXi vSphere universe. Now, in 2020 and beyond, we're going to experience exactly the same phenomenon. So it is going to be a parallel universe, which is in the cloud native world, that's going to evolve and emerge. So we'll see cloud native storage, we'll see cloud native networking, cloud native security, cloud native observability, monitoring, and many other parallel technologies and streams that currently exist in the physical and virtual world. And Portworx is a very prominent player when it comes to the storage offering and turning Kubernetes into an enterprise data platform. So I have been working closely with Portworx for the last couple of years. It's been an absolute privilege for me to collaborate with Portworx, particularly with Michael, on working on the outreach and evangelizing Portworx and explaining how things work behind the scenes. And it's been a great journey to see how this entire, not just Portworx, but how the actual market segment has evolved over a period of time. So I'm pretty excited to show you some capabilities, but a quick disclaimer. Now, this is going to be a very fundamental but very essential building block of running production workloads on Kubernetes. Portworx has an entire data platform starting from core PX storage all the way to PX Central that Michael was talking about, which is going to be the overarching interface and control plane for multi-cloud and managing multiple Portworx clusters. But what I'm going to show you is something very fundamental and one of the core building blocks of Portworx, which is the PX storage. So in today's demo, I'm going to show you how PX storage works and how you can actually use a database like MySQL to run in high availability mode that is fault tolerant, that is durable, that is persistent, and can tolerate a variety of issues that actually crop up when you run in cloud native environment. So let me get started and show you what I'm actually going to configure and what the current environment is. So first thing, I have a simple GKE cluster. So let me show you the environment. So I have 3-node cluster up and running at Google Mumbai region. So this is Asia South 1A, which is the Mumbai region. And I have exactly 3-node cluster that's running. Now, I've already gone ahead and installed Portworx. So if you actually look at the Cube system namespace, in the Cube system namespace, you'll notice that there are a bunch of pods that are running that are specific to Portworx. So there is a daemon set, and if you notice, the Portworx pods that are actually running here are a part of the daemon set, which means they're pretty much installed on every node of the cluster. Then there is something called start and start scheduler, which is another essential element of Portworx cluster, and this basically stands for the storage orchestrator for Kubernetes. And this works very closely with the default Kubernetes scheduler to make sure that the data-centric pods are located exactly on the node where the data resides. So this is how Portworx shows up when you actually install it on a Kubernetes cluster. Now, this could be GKE, EKS, AKS, IKS, Rancher, PKS, it doesn't matter. It essentially runs on any Kubernetes flavor, whether on-prem or cloud or hybrid. And once you have the Portworx cluster configured, you are ready to deploy workloads. Even though this is very basic and very fundamental, you can augment this with many other workloads. For example, we have a very, very detailed deep dive tutorial on how to run Jupyter Hub on Portworx with complete fault tolerance and high availability. And we can also run TensorFlow, Kubeflow, KF serving, and bring in all modern workloads that take advantage of this. So for now, let me show you what it takes to run MySQL in HA. So we have already seen that the Portworx cluster is up and running. Now let me go ahead and create the namespace called PXDemo. And then I'm going to set the context so that I can avoid using -n with the PXDemo namespace. So this basically changes my kubectl context by pointing it to PXDemo. And then I'm going to create a storage class. If you're already familiar with Kubernetes, you know that the storage class acts as the interface. It's pretty much like the driver between the underlying storage provider and the workload. this is like a typical driver, like a SCSI driver that you typically install when you want to access a third-party storage layer. In Kubernetes, this is exposed as a storage class, and this shows up only after you install Portworx storage cluster. So here I'm creating a storage class, and I'm pointing the provisioner to Portworx volume. Now, Portworx is actually available as a part of the stock Kubernetes distribution, upstream Kubernetes distribution. So you don't need to install any controllers or any provisioners, and what it basically translates to is a dynamic provisioning capability. So we use Portworx volume as a provisioner, and then we also pass some parameters like the replication factor as 3, IO profile as database, IO priority as high, and the file system. Now, these are very specific to the workload. For example, we are running MySQL here, so we need more IOPS. So I define the IO priority as high and the profile as DB. And this is essentially a hint to Portworx saying that we need better IOPS, and it needs to prioritize on the IOPS and the queue that is emerging from this workload. But the most critical aspect here is the replication factor of 3. What it basically means is every time we write to the underlying storage, it is synchronously copied and redundantly written to 2 more volumes behind the scenes. It's exactly how Amazon maintains fault tolerance and durability of EBS volumes, which is completely transparent. You never need to worry about where are the other 2 volumes, but it is done behind the scenes. And if something goes wrong, it is very easy to recover. So similarly here, we define a replication factor of 3, which means that we are essentially creating a block level replication, which is going to be written to 2 more nodes. So this is going to give us high availability. Even if we are not configuring synchronous replication or creating a active-active or active-passive database cluster, we can still derive the high availability factor by just configuring this in the storage class. So now it's time for us to go ahead and create the storage class. So now I create the storage class, and when we do kubectl get sc, it actually shows up here. So this is based on Portworx volume, and we have a new storage class. And once we have the storage class, the next step is to create a persistent volume claim. So the persistent volume claim is again based on the high availability storage class we defined in the previous step. And we are also giving it the 1 GB of storage space, and read write once, because we don't want to have read write many here, because this might create some blocking issues and unwanted issues. We are actually dealing with pretty concurrent, transactional, consistent database workload. So we want to make sure it is read write once. And then we create a PVC based on the storage class that we created in the previous step. So let's go ahead and do that. So here we have a new PVC. So this is currently in pending state. In just a second, they should become bound. And once we have that, it actually becomes ready for the workload to get visibility or to have a mount point from this PVC. So now it's time for us to create the application, which is the MySQL workload. And here is the typical deployment of Kubernetes. Mind you, I'm not using a stateful set. Actually, a stateful set is not required, primarily because we have defined the storage class replication factor as 3. And because the storage, the block level storage is being replicated, I can safely run 1 instance of the database, but still get the advantage of running a HA cluster without actually dealing with the complexity and the plumbing required to run a full-blown database cluster. So this is almost like any other stateless workload. We are using a deployment, but we are putting the replica as one to make sure that we are just running 1 instance. And this will also make sure that the Kubernetes controller will ensure that there is at least 1 pod running all the time. That's the advantage of using a deployment versus a pod. And then we are again creating a custom scheduler here based on stock. And what this will do is it will gracefully place the MySQL pod on a node where the data is already located. So in a large cluster, you may or may not have storage configured on every node. Most of the managed Kubernetes services have a concept of a node pool. Now, the best practice is to create a node pool for SSD, right? So I create a node pool of 5 machines and I attach SSD disks so that I get maximum throughput. Now, the remaining nodes are in a part of a different node pool, and they are optimized more for memory because I'm actually running cache and some in-memory jobs. So in that case, I never want my workload to invariably get placed in a node pool or a node that doesn't have the SSD disk and subsequently the PVC associated with the actual pod. So Stork will always ensure that the pod gets gracefully placed on the same node that has the data. And this is how Portworx achieves hyperconvergence, where the compute and storage are co-located on the same node, giving us seamless performance and seamless experience, and without doing any magic in terms of node selectors or creating node affinity, pod affinity. You don't need to deal with any of those complex annotations. You can use Stork, which will do the job for you. So that's how we define MySQL. So let me go ahead and launch the app. It's pretty straightforward. So now we are running MySQL pod. So now when I actually do kubectl get pods, there we go. MySQL is already up and running for the last 7 seconds. So this is now associated with Portworx. So what we're actually going to do is grab the PVC name from kubectl get PVC, and it comes up into the volume here. So this volume will actually have the PVC name associated with the Portworx volume. And now we are going to grab the identifier or the pod name that runs the Portworx binary. So this will help us in grabbing the Portworx pod. So this is actually a part of the daemon set. And once we gain access to that, I'll go ahead and use a nifty binary, a nifty tool called PX-Migrate. Now this lives inside the pod of the daemon set. So what I'm going to do is use kubectl exit into the PX pod to gain access to PX-Migrate, and then we'll invoke volume inspect and pass the volume associated with the MySQL PVC. And this will show us some pretty interesting details. So let me run this command, and now here we actually see that this is the 1 GB PVC, and the format is XFS. HA is 3. That's because we define the replica as 3. And it also shows that these are the nodes on which the replica sets are created. That means there is a 3-factor redundancy without you configuring anything explicitly within the pod or within the storage layer. So this confirms the fact that the MySQL pod is now associated with the Portworx volume. So behind the scenes, what actually happens is every node of a GKE cluster has an external persistent disk attached to it. Now in EKS, the case could be EBS, but in GKE, it's a persistent disk. In Azure, it could be a premium storage SSD. It doesn't matter. So if I attach, let's say 20 GB of persistent disk to every node, then Portworx essentially pools these 3 disks and creates a 60 GB volume for us. And this 60 GB volume is a container native storage volume that no block storage is capable of addressing, or it just doesn't become visible to a cloud native workload. Whereas Portworx will essentially aggregate the volumes attached to every node and creates a logical volume that is a pool of all the storage disks, all the block storage disks that are attached to the nodes. So that's the reason why we achieve high availability and also a kind of a logical view of how the storage is distributed. So now the workload is up and running. So that is like the day 1 operation. Now let's actually move to something more interesting. So this is going to get interesting. So now what I'm going to do is, basically populate some data. So I'm going to move fast here. What I'm going to do is access the MySQL pod, and as soon as I am in the MySQL shell, I go ahead and run some commands. So I'm going to create a database first, and then populate it with some sample data. So if you notice, there are about 7 rows, and I just copy and paste. Then we'll do a select from this table, and there we go. We have some sample data set that's populated with some test data. Now I'm going to do something pretty interesting. So now if you actually see, there are 3 nodes, right? Now one of the nodes, actually when we do get pods with wide output, you see that the node ending with 70M6 is actually running our MySQL pod. Now what happens in real world, in a real world scenario, this node faces a disruption, right? It could get cut off with a networking issue, or the storage might fail, or the OS might just experience some issue and it just becomes inaccessible. So what will you do in that scenario? Well, because we are using Portworx, it's not going to be very difficult in retrieving this. So what we'll do is we'll actually simulate a node failure by first getting the name of the node that is running the MySQL pod, and then we will do what is called as cordon. So in Kubernetes, cordoning a node basically disables scheduling. So when we do kubectl get nodes, you notice that this is disabling the scheduling part of it. That means no new pods will ever get placed on this node. It's a hint to Kubernetes scheduler. But existing pods will continue to run. For example, our pod is still up and running on the same node that is actually cordoned off. But what happens if we go ahead and delete that pod? So what I'm going to do now is actually delete that pod. Now I'm going to put this in watch mode. So watch kubectl get pods. Now currently this is running, and because we are running a deployment with replica of 1, as soon as we delete the pod, Kubernetes does something interesting. So actually let me run this in wide mode so we can also notice the new node. So now I'm going to delete the pod that is running on the cordoned off node. As soon as this is terminated, Kubernetes will go ahead and create a new pod, but on a different node. Now the old pod is gone. The new pod is created, not on the same node because it is not reachable. It is now cordoned off. It is disabled for scheduling, but the pod has been relocated to another node. Now the question is, will the data become available? Will it retain the actual data that was populated in the previous step? Before I go any further, let me uncordon this because we may have some side effects if I don't do that in the subsequent demos. So I'll uncordon it, and then let's grab the pod name and then do a kubectl exec into the pod. So now we are accessing the MySQL shell, and I'm going to access the database. Looks like the database is live. It's still existing. Now I'm going to do a select start from the table, and there we go. Data is intact. This is after the node getting crashed, the pod getting deleted, and Kubernetes placing the pod in a completely different node. It doesn't really matter. The data is still intact, and the pod doesn't even know that it has been placed on a completely different node from the original pod. So that's the beauty of using a hyper-converged storage infrastructure where compute and storage are co-located, and thanks to Stork, which is going to carefully place the pod on the node that actually has the PVC and the volume available. So that's the beauty of using Portworx with the replication factor of 3, and also using Stork as the custom scheduler. So that was the second demo that I wanted to show, which is day 2 operation. And most of the DBAs, this is the nightmare. They dread the database crash or a host failure because it is going to keep them awake at least for next 3 days. But if you use a storage engine like Portworx, you don't even realize. You basically, the moment Kubernetes realizes the pod is unavailable, thanks to the controller and desired state configuration, it basically brings up another pod, and the data actually becomes available immediately in the next pod. Now, the other thing that most of the DBAs suffer from is the dynamic nature of databases. They grow pretty rapidly, and these spikes are very difficult to handle. And in cloud native world, this is going to be further challenging because cloud native is all about hyperscale. You never know when this e-commerce site will really explode and it will start taking more orders, and the transactional database will grow exponentially and the storage might just run out of space. Now, there are two ways of doing it. One is manual. So now what I'm going to do is, again, grab the volume that is running our MySQL pod, um, and then I'm going to basically show you the PX-Cuddle volume inspect. Now, this is currently running 1 GB. I deliberately made it 1 GB. But now what we're going to do is manually expand the size to 2 GB. So now we are basically using the PX-Cuddle binary and passing on the volume ID, which is the PVC name associated with MySQL pod, and adjusting the size to 2, which means now the volume will become 2 GB. So it's pretty clear. Now, this is the first method, and this is very manual. But remember, Michael was talking about something called PX Autopilot. And if you don't want to deal with this manual resizing, you can actually configure a pretty intelligent rules engine that will automatically expand and adjust the size based on the workload characteristics. So if there is a spike in the compute, that is the pause, and that impacts the storage, Autopilot can kick in and can predict that it's going to require additional storage, and it will auto scale the storage. Now think of it like an auto scaling group of EC2 but applied for your cloud native storage. So that is the other cloud native storage ops that you can apply, either manual or using PX Enterprise, and which is the enterprise version of Portworx that comes with this capability of PX Autopilot. Now, the final thing that I want to show you, the fourth demo, is again something very critical, that is basically taking backups and restoring. So now Portworx also supports taking snapshots, and again this is just scratching the surface. This is very fundamental, and Portworx had this capability 3 years ago, and they have come a long way. But since this is the first time that I'm actually demoing, I want to walk you through the very fundamental building blocks and pillars of PX storage. But trust me, this can be taken to the next level with PX-Migrate and KubeMotion. But let me show you what it actually takes to create a simple snapshot. Now, if you're familiar with cloud storage, whether it is Amazon EBS or Google Persistent Disk, GCPD or Azure Disks, you can take a point-in-time snapshot and create a brand new EBS volume from that snapshot. How about bringing that capability to cloud native volumes and creating snapshots and restoring them and recreating the PVC from an existing volume snapshot? So that's what I want to show you now. So what we'll now do is to create a snapshot. So we are first going to create a snapshot from the PX-MySQL PVC. And if you remember, that's the PVC we created for the first time when we mounted this within the MySQL pod. So I'm going to define this saying, grab a snapshot of PX-MySQL PVC. So that's what I'm going to do here. So once I create this, it's going to create a new snapshot. Now I can verify this by running a couple of commands. So now the snapshotting is done. It has taken a point-in-time snapshot. This also shows us that this is currently available and ready to be restored. If you also, if you really want redundancy, you can take this and point it to an S3 compatible storage, and it can actually externalize the snapshot to another region if you really require. So now what we'll do is we will gain access to the current pod, and then I'm going to again access the MySQL shell, and within the shell I'm going to do something pretty crazy. You know that there is a database called classic models. What I'm going to do is just deleting it. So now I have gone ahead and deleted the database, and if you now look at the database, I have dropped a production database while the clients are still connected. This is a sure shot way of losing your job if you're a DBA. But now what I'm going to do is use a special type of storage class, which is called the Stork Snapshot Storage class. It becomes available the moment you install Portworx storage. So using that, I define a new PVC. So here I'm actually creating a new PVC. So this is a persistent volume claim. but there is a very special hint to indirectly to Stark and Portworx, saying that this is not a usual plain vanilla PVC. Instead, please create this PVC based on the previous snapshot. And then you're also giving the storage class name as Stark snapshot SC. This is a big hint to Kubernetes to basically pass it on to Portworx and Stark, and don't create a plain vanilla PVC. So this will basically result in creation of a new PVC, which is containing all the data that was a part of the snapshot. So now, if you do kubectl get PVC, we have two PVCs, one the original, the other one is the clone, and the clone was created exactly 4 seconds ago. Now what we'll do is we will create a new pod, and this time everything remains the same. This is a MySQL pod, but the fundamental difference here is, instead of mounting this on the typical PVC created from the dynamic provisioning process, here if you notice, the original pod before the snapshot was taken was created from the PX-MySQL PVC. Now I'm creating a new pod, a new deployment, and I'm actually pointing it to the clone. So let's go ahead and create this again. So this is going to be a clone of the original MySQL pod. Now I'm going to get the name of the pod. Let's call it as a snap pod, and I'm going to exec into it to access MySQL shell, and I can use classic models, and this is select star from offices. Okay, so now I'm going to run this query again, and there we go. All the rows are intact. Now this is the second pod that's primarily a clone of the original pod before the database got dropped. So this is how you take point-in-time snapshots and restore them. And this is exactly the same workflow that you would use with an EBS snapshot, store it in S3, create a brand new EBS by restoring the snapshot and mounting it to an EC2 volume and pointing the database to it. But that's pretty cumbersome. And of course, you can automate that to some extent, but nothing like using a cloud native YAML file and automate the whole process. So this is how DBAs deal with cloud native storage without ever leaving kubectl. That's the whole idea. So it just aligns with the same workflow that the Kubernetes operators are familiar with, and kubectl becomes your weapon, whether you're dealing with network, storage, compute, or performing security operations. And we pretty much use the same familiar kubectl tool for the entire workflow, from day 1 to day 2 and even day 3 operations of managing backup, restore, and dealing with disasters and disruptions. So that brings us to the end of the demo, and I hope you found this useful. But again, let me emphasize that this is just scratching the surface. Portworx is way powerful than this. We are almost out of time, but I want to thank our sponsors. So Google Cloud for giving me all the credits and the infrastructure for the demos. Everything runs on GKE, thanks to Google. The Newsstack, my media partner, and all the articles and tutorials show up at the Newsstack in a day. Foghorn, one of my clients and also a sponsor of MI2, and Portworx. And I'm again thankful and grateful for Portworx and Foghorn to be my clients as well as my sponsors. And I'm pretty excited to announce the next webinar. So on Feb 20th, I'm going to bring you very exciting capability of Amazon SageMaker called Autopilot. Now, this is Amazon's way of doing AutoML, and they took a pretty unique approach. So I'm going to talk to you about SageMaker Autopilot with an interesting end-to-end demo. That's on Feb 20th. At 8 a.m. PT, 9:30 p.m. IST. You can sign up at mi2.live. So I want to thank Michael for joining me and giving us the overview of Portworx, and also thank him for being a sponsor. And every quarter, we're going to bring you back one webinar on Portworx.
Great. Well, thank you so much for having me, Janikiram. This was a lot of fun.
Thanks, Michael. Thanks, everyone, and I'll see you in the next webinar.